Today we're going to talk about distinguishable arrangements and how to count them. So suppose we have 2 quarters, which we'll label Q1 and Q2, and 1 penny, which we'll label as P. How can you arrange the coins? Well, we could have penny, Q1, Q2, we could have P, Q2, Q1, or we could have Q1, P, Q2, Q2, P, Q1, and then lastly we could have Q1, Q2, P, or Q2, Q1, P. Now, if you just have 2 quarters and a penny, you probably wouldn't see a difference between the first two, or number 3 and 4, or 5 and 6. And this begins the idea of what a distinguishable arrangement is. But to go back and answer our question, how many different ways can we arrange this? Well, we have 3 coins for the first choice, we have 2 coins for the second choice, and we have the remaining coin for the last choice. So using our fundamental counting principle, we would have a grand total of 6 ways to arrange the coins. Now, going back to this idea, if we didn't actually have markers on the 2 quarters, we might not see a difference between penny Q1, Q2 or penny Q2, Q1. In other words, we might not be able to distinguish the 2 quarters. So, the number of distinguishable arrangements would be where we have penny, quarter, 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 penny, quarter, and lastly quarter, quarter, penny. Those 3 would definitely look different from one another. Hence, they are distinguishable. A distinguishable arrangement is an arrangement that looks distinct. So for our last example, we had the 3 distinguishable arrangements, even though there were 6 total ways to arrange them. Alright, we now have the following formula. The number of distinguishable arrangements when you have n objects is n factorial over n1 factorial times n2 factorial all over all the way up to n sub k factorial. That is where we have n1 of type 1, n2 of type 2 in the following fashion. What we mean by this is that in the last example we had 1 penny, so we had 1 of type 1, but we had 2 quarters, and so we had 2 of type 2. Here's another example. Suppose you have 2 bananas, 3 apples, and 4 oranges. There are a total of 9 objects, because we have 2 plus 3 plus 4. We have 2 bananas, so we have 2 of type 1. We have 3 apples, so we have 3 of type 2. And lastly, we have 4 of type 3, or in other words, we have 4 oranges. So, we plug this all into the formula to get 9 factorial all over 2 factorial times 3 factorial times 4 factorial. These are large numbers, but they're computable, and so we find 9 factorial to be 362,880, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. Lastly, when we divide the numerator by the denominator, we end up with 1,260. Suppose we wanted to count the number of distinguishable arrangements of 2 pennies and 2 quarters. We have a total of 4 objects and 2 of each type. So, we would have 4 factorial over 2 factorial times 2 factorial, which would give us a total of 6. We could actually find these 6 because 6 is not a bad number to find. We could have quarter, quarter, penny, penny, quarter, penny, quarter, penny, quarter, penny, penny, quarter, or we could have penny, quarter, and lastly penny, penny, quarter, quarter. Alright, that concludes the idea of distinguishable arrangements.